tough crowd. I think that I've learned a lot already. I had my suspicions, but let me mention several of the things that were said yesterday that I found provoked me thinking. Tim was at dinner. We were talking about your career, and I could be personal. You described it yourself, how you started off in physics, went into engineering at Georgia Tech, hoping to do a PhD, and then turned off, went to Dartmouth for a PhD in physics. Paul, at Grinnell, you worked for Lockheed. Was it Lockheed? Is that correct?
Mark, yes, Mark, yes.
Yeah, right. And that didn't last very long either. Something. And the question that raises in my mind, and it relates to why students turn away from engineering at the outset. Why were you turned off? And is it because of the culture that you confronted at those institutions? Or is it in the content of engineering itself? And I think those, of course, you should separate those. And another question that comes up and is there today, how do you advise students that are coming to this 3-2 that express some interest in engineering? I think you raised some interesting points about, I would say, the ethics of advertising the 3-2 incoming students. There's an ethical problem there. I think there's another one associated with the idea that you could set limits on enrollment for certain groups. But let's leave that aside. But how do you advise students? This is a general question at all levels, at high school. What is engineering? What do you say to them? What is engineering? That's a difficult question, engineering. A light question. Do engineers think differently than scientists? Are these questions, maybe I think they're the wrong questions to ask. Maybe there's so many different kinds of engineering going on. Maybe there are 20% of those participating in engineering jobs don't have degrees in engineering. That's a survey that was done in the 90s. 2 million people, 2 million individuals that were employed in engineering as engineering workers, or had degrees in engineering, that's it, but had undergraduate degrees, and some had engineering degrees. One of the facts that came out of that was 40% of those interviewed at some time later in their career, I don't know, 40% of those that had an engineering undergraduate degree were no longer, they said they were no longer doing engineering. Now, what's going on there? Why do they say they're no longer doing engineering? Well, they're probably not doing engineering, maybe doing management. But I suspect also they're no longer doing what their faculty said was engineering. And I think maybe we should open up a little bit our advising to students within engineering. Engineering education is changing. Engineering is changing. There's a lot of things going on in engineering education. The proliferation of minors at MIT. The scope of what mechanical engineering is broad, we're talking about this year. The legitimacy of doing course 2A now, which was formerly the program for dropouts from course 2 mechanical, hardcore course 2. Now that's a favorite program and legitimate because it allows students the flexibility. Think of all the intercollegiate competitive educational activities that go on. Solar car, steel bridge, Formula 1. Many students in engineering schools do these. Think of all the public service activities. Students want to do good. Think of all that. Generally, those experiences don't get any academic credit. Something's going on, but the students are doing it. And they'll tell you that these are some of the richest engineering learning I've done. Well, that's kind of off my subject because I want to sort of turn the tables. And first I want to mention, I encourage you maybe to attend an ASEE meeting, Emeritus Engineering Education meeting, to get a sense of, there's a lot of people asking interesting questions there about what is engineering, just how to teach engineering. Sheila's giving a workshop down there
With all
research.
participants in these alternate courses.
Right.
A whole day workshop.
Right, so that's June 25th to 28th, probably a little too late to schedule that. But there's also another one there by Juan Lucina out at Colorado School of Mines on social equity and problem formulation in engineering. I look at the description online. But my topic is, I think, more relevant, hopefully, to what you can do here, and that's how do you bring engineering into the liberal arts? And I have David Druitt down and I have this project funded by NSF, and it's meant to infuse engineering into regular courses in the liberal arts, in the humanities, arts, and social sciences. If you forgive me, I'll use liberal arts for shorthand for humanities, arts, and social sciences. Courses in history, anthropology, political science, literature. It will require the participation of people, of faculty from science. But I'm thinking of these as being, these courses being rooted in the liberal arts, bringing to bear the perspective of the liberal arts onto engineering. The word was, I think, meta-engineering was used. That's a phrase I like. To have students engage in engineering, thinking, doing, but the main purpose is not to make them engineers so much, but to know how engineers think and act, and to reflect on those experiences. And I have some modules to show you for that. It's also, I think, in our proposal, in the article that Diane referenced, in our design plan, we don't really design a curriculum. We set out two functional criteria. One, whatever is done, it should infuse engineering into courses in the liberal arts. Okay, talk from that perspective. Two, it should engender a sense of community among students. And I think this is probably characteristic of your schools anyway, and it's characteristic of your program at Smith. But I think it's not generally a characteristic of program in an engineering school. Maybe it's true at Swarthmore, probably Lafayette as well, or Bucknell. But generally at a large research university, community is not the word that's used. It's used in sort of by the students, behaving right, or are they healthy? I might say a word about the scope of our proposal. Who is maybe a client, a user, a customer for our proposal? I'm here with you from the liberal arts. We're also talking to people in community colleges. Why can't, there are liberal arts community colleges. Maybe some of you know faculty there. They probably went to some of the same programs you went to for a PhD. There's competence there that's probably not recognized outside of the community college environment itself. So there are programs there, an associate's degree, kind of like a 3-2 program maybe a liberal studies and engineering program, 3 years, and then on into a university, better prepared to take on the engineering. Of course, some students already do that. But, the other phrase we use is smoother pathway. I have worked at engineering education, and teaching it for quite a while, and I was responsible, or I was a PI of one of the NSF-funded coalitions in the 90s to make design a more legitimate engineering educational activity. And I think in some ways we were responsible, our coalition of 7 schools, for transforming at least the freshman year, allowing things like what Susan does to be a legitimate activity. Take the old, invite the industry people into lecture to the students, make it into something where students are doing something actively, some kind of design exercise. Also teach them a little CAD. So I'm all for design, the openness to that. The openness experience of design is halfway there. The engineering sciences are essential, necessary to engineering work, but they're not sufficient. So let's get on to the smoother pathway. There's a lot to be said here, but let's get on to the next slide, please. All right. Here is a slide from one of the modules. It's Galileo and Two New Sciences. And it's meant for dual use in a course in the history of science or in a course in statics and strength of materials. It has been used, an earlier version, in the teaching of a sophomore level statics and strength of materials at UMass Amherst by a colleague of mine and a colleague at MIT in the same course. Okay? I can't show you, I could show you the whole module. The video that was up here before I spoke, that was steel construction of Hadley Library. That was South Hadley Library. That is a module in this, that's a unit in this module. But the purpose of this module is to infuse some engineering into a course in the history of science, let's say. So here is a section from Galileo's Two New Sciences in the second day when he looks at the resistance of beams to fracture. And he starts with this analysis, this thought experiment on a rope. Where does it break? And so we're going to do that. And I'm going to be Simplicio, and Diane's going to be Salviati. I mean, there are three people in the dialogue that those of you that may not know Two New Sciences or the Copernican piece too. Salviati is Galileo. Simplicio is a defender of Aristotelian thinking. And Sagredo is a wise friend. Sagredo doesn't figure in here. So, I'm Simplicio. I will start. Simplicio. Before proceeding further, I should like to have one of my difficulties removed. Up to this point, you have not taken into consideration a certain other kind of resistance, which it appears to me diminishes as the solid grows longer. And this is quite true in the case of bending as in pulling. It is precisely this that in the case of a rope we observe that a very long one is less able to support a large weight than a short one.
I fear, Simplicio, if I correctly catch your meaning, that it is the particular you are making the same mistake as many others. That is, if you mean to say that a long rope, one of perhaps 40 cubits, cannot hold up so great a weight as a shorter length, say 1 or 2 cubits of the same rope.
That is exactly what I meant. As far as I think, this proposition is highly probable.
On the contrary, I consider it not merely improbable, but false. And I think I can easily convince you of your error. Let AB represent the rope. Do we have another slide?
No, this is it.
Yeah, we have
See
it.
the AB?
AB, okay. Let AB represent the rope fastened at the upper end A, at the lower end attach a weight, C, whose force is just sufficient to break the rope. Now, Simplicio, point out the exact place where you think the break ought to occur.
Let us say D.
And why at D?
Because at this point, the rope is not strong enough to support, say, 100 pounds, made up of the portion of the rope DC, DB, and the stone C.
Accordingly, whenever the rope is stretched with a weight of 100 pounds at D, that's where it's going to break.
I think so.
But tell me, if instead of attaching the weight at the end of the rope, B, one fastens it at a point nearer D, say at E, or if instead of fixing the upper end of the rope at A, one fastens it at some point F, just above D, will not the rope at the point D be subject to the same pull of 100 pounds?
It would, provided you include with the stone the portion of rope EB.
Let us therefore suppose that the rope is stretched at the point D with a weight of 100 pounds, then, according to your own admission, it'll break. But at FE is only a small portion of AB. How can you therefore maintain that the long rope is weaker than the short one? Give up, then, this erroneous view which you share with many very intelligent people, and let us proceed.
So it goes.
Good job.
I don't know if you read the dialogue or Two New Sciences or his treatise on Copernicus, but it's a very interesting, well, really more good literature. And a matter of fact, that's one thing you could take as a subject for discussion with this module. Any of the history of science could be a literature course, narrative and technology or something. But, then you bring up your engineering colleague and you say, well, let's test it out. Let's see if he's right, all right? Let's go down to the makerspace, get us a rope and a stone, and do this experiment, right? Okay, so anyone that does an experiment knows that when you do an experiment, you want to know the answer before you start. So you have to figure out what's going, what are the ingredients of this experiment? Okay, what's a cubit? Anyone know what a cubit is? Go ahead. Yes.
Elbow to fingertip.
Yeah, from here, about here, about 18 inches, I guess. All right, that's good. So we know how long the rope was, 40 cubits. That's a pretty long rope. All right. We got enough space here, I guess.
You might need the Leaning Tower of Pisa for that.
You didn't do that. All right, 100 pounds. Have the students go to the web. I mean, let them do that for the cubits too. That's another resource that's there, right? Let them flail around on the web a little bit and try to figure out with 100 pounds what's then and now. Well, it turns out it's roughly the same, at least for our purposes. All right, so what kind of stone? What's the weight of the stone? Well, we said, let's just check that out. We know the specific, let them check the specific gravity of stone, about 2.5. So what's the density of water? Every engineer knows it's 62.4 pounds per cubic foot. Okay, I'm sorry, you people you physicists that love the metric system. We engineers haven't been able to make a conversion yet. I have another unit on that in another module. Why that is so? It's a cultural problem. So we figure out the size of the cube based upon this information that we've derived from the web. We find that x is about 3/4 of a foot. Well, that looks about right. All right. But then we have to figure out the rope. All right. What's the diameter of the rope? I say it's 1/10 of the 3/4 of the foot. So I'd say it's 1 inch diameter. 1 inch diameter. I've been down to the docks like Galileo was, and down to the workshop. So I know the halts are maybe 1 inch diameter. Okay, and I said, okay, what load do we have to apply to break it? You go to the web, and you look and you find manila rope, and you find a 1 inch diameter manila rope takes 8,000 pounds to break it. What do we do? What do we do? Why are we doing this? Well, here's why we're doing it. We can raise the question, did Galileo do the test? Probably not. It's a thought experiment, right? Does it matter if the thought experiment can't be experimentally verified? All right? Okay, let's go on. Think about that. I don't have the answer, but it's something that you should discuss in your course about engineering infused into a liberal arts course, into a history science course. Okay, let's go on next slide. This is part of the same unit, and this is the piece that has been used. It's from a little bit further into the tune-in sciences, and it includes Galileo's proposition, he calls this, about the breaking sense of the cantilever. And he effectively models this as a lever, you see, with a length BC being one lever arm, a fulcrum at B, the bottom of the loop, and halfway up, AB, he pictures an internal resistance, of internal force, balancing this force here, force to the wing. Get that picture? Is that somewhat clear?
We call that a moment now.
What? So, what's the ratio of this load to the internal resistance? Well, it depends upon the length. It's half the length AB to the length BC. It's a law of the lever, right? And there he says it here. That's that. Okay. Now, here's the step he takes that I think is a truly an engineering thing. He says, if we define absolute resistance factor as that offered to a longitudinal pole, so take this beam out there, put it in a tensile test machine, and pull it until you break it, okay? Then you have a measure of the force, the absolute resistance. With that knowledge, for that beam, you can then predict what end weight it will take to break the beam. Beautiful. But that's an engineering kind of step there. He also has some concept of this stress. He doesn't say stress, but he talks about fibers in this beam. And he says how that absolute resistance is distributed over bunch of fibers. So so with this, he's able to derive a whole set of relationships about beams of double the length, twice cylindrical beams, so beams even on different supports. It's all wrong. It's all wrong in the sense that his first original analysis, it's off by a factor of 3 compared to engineering beam theory, which continues internal stresses. Well, it's not quite all wrong, because if you take the ratio of the failure load of this to the ratio of the failure load of the beam of twice the length, his ratios are correct. So his scaling laws are correct. So here we have a theory, an engineering beam theory, in prototype form, let's say, in which some of it's wrong and some of it's right. Now, what do you do with that? All right? How do you deal with that? What about our theories today? Are we sure they're fully right? What are all the assumptions that are made? Okay. We move to the meta level. We say, what's going on here in the way engineers think about problems? What are the limitations? Next slide, another module. This one is, this is meant for a course in cultural anthropology and fluid mechanics. And it's just working this up, so it's not available on. By the way, the Galileo module is available online on the edX platform, and if you want to have instructions to access that, I can give you those instructions, and it's free. You don't have to take the course, there's no course. It's an experimental development. I'm working with MITx to put these modules up there, to make them available to anyone who wants to take them and use them as their own. Okay. It's kind of a new thing. Get away from the idea of a MOOC with the talking head, with a faculty member doing their thing within the box of the textbook and entertaining you for an hour or half an hour or so on, to a presentation of source materials, provide hopefully provocative questions. But you take it and use it and amend it as you will. So I'm working on that. So here's cultural anthropology and fluid mechanics. I'm sure you have anthropologists on your faculty. This is the Zimbabwe bush pump. They're contemporaries, roughly. This has been around for a longer time. There's been continual development, innovations in making this work better in Zimbabwe. It's kind of a national standard. The person that is responsible in a way for shepherding it through these innovations is a white person, Peter Morgan from South Africa. But it's adopted by the village. It's maintained by the villagers. All right. It's as I say, it's fit with standards. I'd say it's a good pump. It's an open pump in a way, because it is amenable to change, to innovation, to maintenance by people other than the person who made it. This is the play pump. Has anyone seen this? This is a wonderful machine, all right? It's a merry-go-round. And the idea is that children will rotate this. And inside of this blue box is a mechanism that the below ground is essentially the same as this. It's a displacement pump that pumps the water up into a tank, 2,400 liters. And then you have a tank. This play pump made a big splash. It was a huge internet phenomenon. Frontline, PBS did a video in 2005 showing the maker of this pump, Trevor Field, was a South African. He was a marketing person. You notice there are billboards here, you see, and the way they're supposed to finance the maintenance is you rent out billboard space to people. So huge event on PBS. President Clinton allotted $16 million to development. Laura Bush endorsed it. There was a huge donor. They set a goal, 60 million or something. A huge donor output over the web. And then the problems started to appear. Very good. Well, someone figured it out. And this is an exercise for the students. How many hours did the students have to rotate that pump at 16 RPM, which was not right, to fill the tank? Something like 10 hours. Would you like our children in our schools to be working 10 hours? When are they going to go to school, right? So there are questions here about the design, but anyway, this didn't really last in its enthusiastic form. So, raise the question, what is a good pump? And I want to say this was all done with good intentions. Everyone along the line, good intentions. The maker of it, he was going to solve the water problem. President Clinton, the donors, good intentions, all the way through. Okay, that's evidently not sufficient to have a lasting, sustainable effect. Now the engineering, so that's meat for anthropologists, all right? It's also, Amy, I think you'd agree, there's some good fluid dynamics here, right? You can check them out, see what it takes to, how many strokes per minute, per hour, how many rotations in order to give the 1,400 liters per hour they advertised. But there are other interesting things here that aren't generally analyzed. What's the work, what's the energy required, what work is done? What power is required? Here you have a system with rotary inertia, right? And you have impulse rotary inertia. How do you look at that? In fact, you're probably doing a problem that you won't find in a physics text or in a mechanics text or in a dynamics course in engineering. I don't know, maybe Susan, you can find me one. But, you know, it's an intermittent kind of thing. There's a mechanism here which you can trace the forces. That's an interesting exercise. And you have an intermittent kind of operation here of forces. So what does it mean to speak about power in that situation? Yeah, all right. Energy? Okay, anyway, these are all questions that you need an engineer in there, probably to provoke that kind of question. All right, my last module. This is an exercise that's meant to be used, of course, in gender and science for engineering and in computer science. I'll read it. In this exercise, you implement it, or do you want to read it? I'll read it. You implement a solver for a reducing ordered selection problem. And as an IT engineer in a small company, Mary has just found early that the company plans to lay off one member of the department containing N people every week until only the best is left. In order to find the best logician, they are letting everyone choose a position on a list numbered from 1 to N. They will be removing every kth person until only one remains. Mary knows that she can come up with the best solution to this problem quickly and keep her job. Your job is to do likewise. And then, for example, okay, that's the computer science problem. That's an interesting, and I think there is a computer science in the room, right? It is a real problem, right? And it's not an easy problem. It's not the first problem to give students. In fact, and one of the ways to solve it is with recursion. And recursion, I think, is notably in the teaching of students, as I understand it. I'm not a computer science. A difficult concept to get students to recognize what's going on. But you need not use recursion. You can do the case when k is equal to 2, like he gives an example here, and you could probably do it with the manipulation of lists, you know, and I think you can teach that pretty easily to students that only have algebra, or whatever. It's not even calculus or anything like that. So there's a computer science problem here. So that's the computer science exercise. Give students the experience in your liberal arts course and your gender and science course. What is it that's so attractive about solving problems in engineering? Give them the sense, give them a way, give them the tutoring, so that they experience both the frustration and the joy of getting a solution. See the power of the computer in giving you what? A result, an answer that tells you where to stand in line. All right? Okay. What does Mary have to do with it, though? You know, let's go to the gender and science bit. Why is she there? It's wholly gratuitous. Furthermore, there's another problem here. I'm a student now, of course, in gender and science. All right? What's Mary doing there? You know, what is this? I got to find the best place to stand in line. But Mary's already got that place. what am I going to do? Now, in the essay I wrote about this, I turn and say, what would happen if students in your computer science course raised that question? What do you think? Would it be laughter? Would you say, you shouldn't be here in this course? There's, in the essay I report about, and on the module to be, this is again a module I'm making, I quote Aaron Jack, is that how you say it?
I think so.
Jack, who has written about the depoliticization of engineering problems, how context is missing. And I think this is a good example of that. The belief that engineering work should be disconnected from social and political concerns because such considerations may bias otherwise pure engineering practice. Through the lens of this ideology, the social and political forces that are at the core of all engineering work are made invisible, leading many engineering students and practitioners to believe that all messy social aspects of life should be left at the door of the engineering work. It's like, I like to think of it in terms of putting on a special pair of glasses that only let you see the computer science, that filter out the Mary, all that stuff. Just like in Galileo, a pair of glasses, you filter out all that fancy stuff and see a lever. So let's leave Mary out. But even then, forget Mary, forget the bit trying to attract women into computer science.
Yes.
What kind of a firm is this?
Yeah.
You know, you're sitting around and you're watching, you know where to stand, but you're watching every week one of your colleagues slaughtered. Is that what engineering work is like? You know, Google evidently, I've heard the anecdote is, they hire, put you in the cubicle, and then they wear you out, and you're off. Right? That's a story, but don't believe that. But there's something to talk about here, I think, or something to discuss. And that is, does the narrative of an engineering problem statement, does it, as Chet would ask, is there gender encoded in the statements of the problem? So, all right, that's all I have.
Thank you.
I guess I have one final slide, just to get back to the screen. And what I would say is I hope that you see what I mean by infusing engineering into a liberal studies course, liberal arts course. Just at the course level, how it might to be done in a wide range of different kinds of courses. I have another one on government and chemistry lab that's related to a instrument used to prove that somebody was driving drunk. All kinds of questions about instrumentation and about where authority in science lies. So that's the idea, is to take a regular existing course and somehow encourage the collaboration. The whole course isn't this. The humanities is still driving it. Encourage the collaboration of the professor in charge of, say, the anthropology with the engineer to bring in the fluid mechanics and participate in the discussion, the entire discussion. Ideally, it could be the whole program. It could be the 3 years of a 3-2 program, which might, well, I leave that. But anyway, I just want to give you an idea of what I meant by infusing engineering into liberal arts. Yeah.
Questions for Larry?